I keep trying to think of clever intros. I got nothing. My name's Dave. We're learning Pico-8. Usually we're at pico-8-edu.com. Today I'm using the premium version. I'm using the full version. Today we're going to make breakout. Now, I fully believe you have all the tools you need to make breakout using stuff that we've already talked about. And also you can get a breakout tutorial anywhere. I want to do breakout in a little bit of a weird way. Maybe it's not the optimal way, but you're going to learn some new stuff that's going to be useful, and we're going to come up with something a little wacky. First, I want to review axis-aligned bounding box collision. I feel like I was moving little pieces of paper around before. It was a little muddled, so I made this little visualizer. If you have two rectangles and they have the same rotation, and you want to know if they're colliding or not, you got to do 4 checks. So I've got this rectangle that'll move around. And you see it's being eliminated right away. Because if we ask, is the right side of R1 greater than the left side of R2? The answer is false. So it's just, we know it's not colliding. If that's true, we go to our second check. Is the left side of R1 less than the right side of R2? So we can see that is false. So on our second check, move on. It's not colliding. Now if I move over above it, you can see we have to do a third check. Is the bottom of R1 greater than the top of R2? So that's our third check. It's false, not colliding. And you see if I move over, we're only doing 1 check. Move over this way, only 2 checks. Fourth check. Is the top of R1 less than the bottom of R2? And once again, you can sort of see how optimized this is. So we're doing as few checks as possible. And then once we hit, when you collide, all those checks are true. And so if the logic gets through all those ands, you can return yes, it is colliding. And you can do those 4 checks in any order. I like to optimize a little bit sometimes to put the most likely one on top. So when we were doing Flappy Bird, I did it like this because the pipes were usually to the right. And so a lot of the checks they only had to do 1 check. So I'll probably post this little cart somewhere so you can play with it. Yeah, that's enough of that. Let's make breakout. I've prepared some sprites already. We've got our ball. I made this ball kind of an odd size, literally. It's 1, 2, 3, 4, 5, 6, 7 by 7. The reason for that is, so if you imagine you have like this middle pixel, and then you work out from there a radius. So a radius of 1 is like this. A radius of 2 is like this. If you want to do an even size sprite, the middle is here, and it's like actually between pixels. And you wind up doing like fractional pixel points. I just found with my experimentation here that the odd size worked nicely. And then I have some bricks down here. Each brick is 2 sprites. And while you're drawing this, you can take this slider and sort of increase your view. And so you want to take up like the upper half of this, and you can make this really big if you want to edit a lot of sprites at once. We have 5 bricks, and then this like broken variant of this brick. And you can make these look however you want. Yeah, let's write some code. In our draw, I'm going to throw in a CLS of 14. So we get a nice pink background. I'm going to make a tab. I'm going to put physics here. And in our next one, this is where the paddle's going to live. Function paddle new. It's just going to return. We'll give it a position halfway on the X, Y towards the bottom of the screen. For its velocity, I'm only going to give it a dx because it's only going to move back and forth. Give it a width of 16 and a height of 3. Now I'm going to be doing things a little differently from how we've done them before. Everything in our game, the position is going to be the center, and we're going to draw around that. And so our width, just to make things easy, our width and height are actually going to be half of the width and height. So we've got that center, and the width is going to be like what's over here, what's over here. You'll see. Paddle update, pass in P for paddle. Paddle draw, P for paddle. I'm just going to use simple rectangle drawing to draw this paddle. First we're going to draw a fill, and then we're going to draw an outline. P.x minus P.width, P.y minus P.height, P.x plus P.width, P.y plus P.height, and I'm going to do -2 just for a little shading effect, sort of. And the color will just be 7. And I'm just going to copy this down here, make it just rect. That, and the outline will be 1. All right. In our init, we're just going to say pad equals paddle new. Down in our draw, paddle draw pad. In our update, paddle update pad. Okay, there's our paddle. Now we want to control it. We're going to have a little physics action on this, and we're gonna do it in a kind of old school way based on code from like classic like NES games. I think it's gonna feel cool. I think it's gonna be snappy and nice. It's not gonna be like supremely realistic, which you could do with like relatively the same concepts, but our numbers are gonna be a little different. So we want acceleration. I'm gonna use these fractions. They're just numbers that I think are like easier to use conceptually for me. And again, I got to make a video about this, but this is how I've been doing it lately. This is kind of the old school way. So this is acceleration, which is like when I press a button, how fast it starts speeding up. We covered this with the gravity in Flappy Bird, and this is going to be like acceleration we control. We want to brake. This is our brake force. If we're like headed in one direction and we hit the button go in the other direction, we want to apply like additional force so that it feels like we're slamming on the brakes and getting to go the other way. We need friction. So like once we keep going, if you let go, it'll slow down and stop. We want a top speed. So you can accelerate to a point, but then you won't get like completely out of control. You'll put a limit on that speed. And this is a weird one. Restitution. This is a physics term. You know how when you bounce a ball, it bounces less every time until it doesn't bounce anymore? I want our paddle to sort of bounce off the sides a little bit, but I don't want it to be the full force. I don't want the sort of reflected motion to be the exact same speed. I want it to be like half the speed, and then it'll hit again and do half of that, and it'll just kind of go like da, 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 da. So down in the paddle update, I want to get input if button left nx minus equals 1, just copy that, plus 1. First thing we want to do, apply acceleration. So take our x velocity and add that input times the acceleration. If we're doing input that's the opposite of the direction the paddle's moving in, we want to apply that braking force. So we're going to do if sgn p.dx. And let me show you, we can do help sgn. Sgn is short for sign, S-I-G-N. The sign is basically whether a number is negative or positive. So if we do like sgn negative 500, it gives us back negative 1. Positive 500 gives us back 1. And the sign of 0, the sign of 0 is weirdly 1. I kind of disagree with that. But it is what it is. We could write our own sign function if we wanted, but good to know. We've got the sign of our paddle's velocity. If it's greater than 0, this will give us 1. If it's less than 0 going left, it'll give us negative 1. We're going to use a tilde equals. The tilde is Lua's way of saying not. So if we want to check if something is true or is equals to, it's the two equals signs, right? Not equals is tilde equals. And I think let's do this. So is not equal to nx, then p.dx plus equals nx times p.break. So we will just apply extra force, extra braking force in the direction we're pressing. I kind of just want to test something here. So we will do p.x plus equals p.dx and run it. All right, so it is working. I think Pico-8 lets us do, in most programming languages, the not is an exclamation mark. It's easier to type. I have this tiny keyboard and I have to hit like the FN key and shift and escape. It's bizarre. I much prefer using exclamation point. I think this should just work exactly the same. All right, yeah. Pico-8's nice. It's like, hey, Lua, you're a little weird about some things. I'm just gonna clean it up. We wanna apply our friction. We're gonna do if ABS p.dx is greater than p.friction, then ABS means absolute. It's the absolute value. If I do the absolute value of 100, it's 100. If I do the absolute value of negative 100, it's 100. All absolute value does is it gives you that number you gave it always positive. We're going to do p.dx minus equals sine of p.dx times p.friction, else p.dx equals 0. The absolute value of our velocity is always going to be a positive number. So it won't care if we're going left or right. It'll just give us a positive number of like how fast we're going. And if it's greater than our tiny friction amount, we want to take our velocity and reduce it by that friction amount. And we got to have that friction amount going in the correct way. So we're going to get the sine of p.dx. Now, because of that quirk, where if our velocity is 0, sine is still going to give us 1. it's going to always like move it a little to the left if it's 0. So like, I just want it so if it gets down where it like is close enough, we're just going to set it to 0 and stop it. And now you can see we get it going and it slows down and stops. Last thing I want to do in here is limit that top speed. I'm just going to do the mid. Remember we used that a while ago. P.dx minus P.top speed. P.top speed. And getting a little long here. I'm just going to do that. So this is just returning that middlest value. If dx is between the top speed going to the left and the top speed going to the right, it'll just give us back the dx. Otherwise, it limits it. So I think that feels about right for what I want. You can tweak these numbers all you want. Make it feel the way you like. So this is the way we've structured our game in the past, where we have this sort of module and we'll have a function to create our thing and an update, and we pass in the thing. In a draw, we pass in the thing. And in our game loop or our scene, we call those functions and pass in the thing. This is great. This is a great way to do it. Sometimes you want a system that's more flexible, not necessarily more optimized, but you can do some cool stuff. So remember when we were talking about variable types? We had numbers, we had strings, we had booleans. We also had functions. A function is a variable type. And so we have this table that's full of variables. We can put a function in our paddle as a variable. This is a concept called methods. So we can say paddle.update is equal to paddle update. And now, usually we always see functions with parentheses. Parentheses are there when we are declaring functions or creating them. Parentheses are there when we're calling functions, when we want to use them. Here, we're not doing either of those things. We are declaring a variable called update in our table, and we are assigning our paddle update function. So we're saying this variable sort of points to this function. We can do the same thing with draw. Now, how do we use this? Instead of paddle underscore update and pass in pad, we have our paddle table as pad. So we do pad dot update pass in pad. These two lines are doing the exact same thing. We've just stored a reference to this in a variable inside this table, and we're using it with these parentheses and passing itself into it. You want to get nuts? Let's get nuts. You might be asking yourself, all right, we're already writing pad here. Why are we writing pad again here? Shouldn't it just know? There's a little something. It's a term called syntactic sugar that Lua lets you do. Instead of pad dot, you can write pad : update, empty parentheses. All this is doing, it's a little shortcut. It's saying, you know that function that I'm holding, that this table is holding, I want you to access it. And the first argument is going to be itself, the table itself. So if I delete this, I can do pad : draw. Same exact thing. You might be asking, what good is that? We'll get there. Now I'm going to be structuring this project in a way that you don't really have to structure breakout. But I think it'll be useful. I think it'll be interesting. And you might be able to envision how this could be helpful for something more complex. We are going to make a table called ents, short for entities. You could call this like objects. You could naming things is hard. I like ents. It reminds me of the tree guys from the Lord of the Rings or whatever. What we're going to do, we're going to make one table that is kind of like our world. And we're going to just throw everything into it and run a little simulation and just let everything kind of bounce around off each other without us kind of hand-holding everything in it. So this is our entities table. I want to put walls around the outside. We're going to do add to ents, comma, make our table. And we could make a tab for this or whatever, but like we're just setting this up at the beginning. I'm just going to throw it in here. Now remember everything in our entities, just so we can sort of like churn through them easily. We're setting the X and Y to the center, and then that like width and height sort of expands out from that. So our left wall, we're going to put it at X equals -16, Y equals 64, height is equal to 72, so it'll be like longer than it needs to be. Width equals 16. So it's like, it's got some thickness to it. Our second wall is to the right. I don't want to have to do math. So our screen size is 128 pixels. The leftmost pixel on the screen is 0. The rightmost pixel on the screen is coordinate 127. We're going to do 127 plus 16. Keep that 64, keep that 72, keep that 16. That'll just be on the right side. We want the top middle 64 minus 16, a height of 16 and a width of 72. The bottom position is 64, 127 plus 16, a height of 16, a width of 72. Back in the paddle, scroll down. I'm going to get rid of this line, the p.x plus equals p.dx. And we're not going to be able to move anymore. What we're going to do is every entity is going to do its own thing. It's going to sort of figure out what it wants to do. It's going to have its velocity, its position. And then we're going to build a little system that churns through every entity and moves it for us with collision. So the entity isn't really going to move itself. So here in our physics tab, let's make a function to move an entity. Just call it move. And we'll take in the entity and a dx and dy. And we'll do e dot x plus equals dx and e dot y plus equals dy right at the start. And then we want to check that entity's collision against everything else in our physics system. We'll do for O for other in all ents, our entities table, do. We don't want an entity to check against itself because it's also in the table. So we'll just say if O does not equal E, so if that's not me, then, and we'll just do if collide, and we'll have to write this function, and we'll pass in the entity and the other, then. Now, we covered collision detection, and we talked about it at the beginning here, and that's kind of the easy part. The hard part is called collision resolution. What do you do with two things when they hit each other? And we've handled that a little bit, like when we put bounds on the screen and we had things stop when they tried to go off the screen. That was really simple collision resolution. Just limit its position, don't let it go any further. This one's going to be a little more complex. And we're going to have to write it. We're going to resolve. We're going to pass in our E entity, dx, dy, and our O. And I think once we have that collision, we don't really need to check all the other entities. We're just we're gonna stop this like the moment it hits. So right here we can just do return. Stop checking. Okay, now we have to write collide and resolve. Function collide takes in E and O. We're just going to do return E dot Y minus E dot H is less than O dot Y plus O dot H, and E dot Y plus E dot H is greater than O dot Y minus O dot H, and E dot X minus E dot W is less than O dot X plus O dot W, and E dot X plus E dot W is greater than O dot X minus O dot W. Hopefully that makes sense. You can review like the beginning of this video if you're like, huh? It's doing our thing, checking the sides, seeing if it's all, if you're hitting. Next, we've got to resolve. Okay, this is gonna be the weird one. And there's a bunch of ways to do this. And there are realistic ways to do this. And there are gamey ways to do this. And I'm gonna do like kind of an arcadey version of this. I'm gonna do a version that works for what we're doing here. Now, when we move, I found it works best if you check X movement and Y movement separately. So something might be moving diagonally, but we're going to move it on one axis first and check, and then move it on the other axis and check. This isn't the way you always want to do it, but like for our purposes here, it's going to eliminate some bugs. It's going to make things feel right. This is the way things work in the code in Celeste. If you've ever played that, the creators of Celeste are much smarter than I am. And when I've made platformer code and experimented with things, I've found it holds up. This is generally a good way to do it. We're going to write this code in a way where we kind of assume one of these, we're going to pass in 0. So we'll say if dy does not equal 0, then we're moving vertically. Else if dx does not equal 0, then we're moving horizontally. Let's focus on the horizontal first, because that's the way our paddle is moving. And we wanna hit the walls. If dx is greater than 0, that means we're moving to the right. Else, we're moving to the left. So at this point, we know we've collided with something, and we're probably overlapping it. We want to move back a little bit, so we're just right on the edge. So we're going to do set the x of our entity to other.x minus other.width minus entity.width. We want to be right on the edge. We get the center, the other.x minus the other.width minus our width. That's where we want to be. For moving left, e.x equals o.x plus o.w plus e.w. So it's like the other way around. We're moving this way. We want to move back. Now, because we're going to be putting a lot of objects in here, they're not going to all act the same way or have the same properties. So we're going to do some checks. So this is going to be what happens after you hit. You want to bounce off. So if our entity even has an x velocity, then e.dx times equals -1. So we want the velocity that's going in this direction to be reversed, so it bounces off. I think we can test this out. Let's just hook this up real quick. After our update, I'm going to do move pad.dx 0. Great. So you got that bounce off the side there. It's adding that velocity. It's checking everything else. When it hits a wall, using our collision detection, it resolves it by moving to a place where it's no longer colliding and then reversing that velocity. Now we had our restitution variable, remember? Because we don't want the bounce to be quite as speedy as we were going. I'm going to do a little trick up here. Local rest equals entity.rest or 1. This is a fun little bit of Lua logic. We make this local variable rest. If our entity has a rest variable in it, then it just sets our local variable to that value. If this doesn't exist, if it's not in the entity's table, it's nil. Nil is evaluated the same as false. Our Boolean values, true and false. Nil can also be read as false. So if this is false, then this OR logic says, well then, rest is equal to 1. So later we're going to have other bounces in the game. And we don't want those bounces to be reduced at all. And so we just won't give those entities restitution, and it'll set this value to 1, and it won't reduce the bounce at all. But if we do set the restitution, then it will override it here. Cool little trick. And you'll see this a lot if you want to do like optional arguments, but we won't get into that yet. So here, instead of 1, we'll do times equals negative rest. So you can see the bounce is like, it's just kind of a little nice effect. Like we really feel like there's an impact there, but it's not like too much. If we like let go of the button, we can sort of bounce off it a bit, but it's not nearly as big of a bounce. Okay, we basically want to write this again up here for vertical. And we'll, I mean, the ball is going to bounce vertically too, so the ball is going to be part of this system. So if dy is greater than 0, then going down, else we're going up. E.y is equal to O.y minus O.height minus E.height. E.y is equal to O.y plus O.height plus E.height. It's basically the same thing, except instead of stopping here or stopping here, stopping there, stopping there. And we bounce. If E.dy, then E.dy times equals negative rest. I don't think anything will be using restitution that's bouncing this way, but just in case we want it, we'll leave it in. Let's make a new tab for ball. Function ball new, an x, a y, a dx, and a dy, so we can give it a position and an initial velocity. Return table, x equals x, y equals y, dx equals dx, dy equals dy, width equals 3, height equals 3. Now here's our dirty secret. The balls are actually going to be calculated as squares. That's the way they did it in old school breakout. It kind of makes all of these bounces really predictable. It's unrealistic, but it's fun. It's an arcade game. And we could have just radius, but since we want all of our entities to sort of be the same, we're going to treat it the same. We're going to have separate width and height. We're going to give it an image, sprite. We're going to give it a draw method, which we're going to write in a minute. Function ball draw, taking B for ball. Sprite, b.image, b.x minus b.width, b.y minus b.height. Let's go back to our main here. So we set up our entities table. We add our walls. We create a paddle. What we want to do is just add our paddle to that entities table. Now we're going to make a ball. We're just going to add ents ball new 64 64 middle of the screen. We'll do 0.5 for the x and 1 for the y, so it's going down and to the right a little bit. Now down here in our game update, instead of calling the pad update specifically and then moving the pad specifically, I'm going to get rid of this. We're going to do update all entities. We could do for e in all, but right now we're going to do for I equals 1 octothorpe hashtag ents do local e equals ents I, and we're going to do if parentheses e dot update. So if it has an update, then do e colon update. So this will only run if we've made an update function for our entity. So like the walls never update. So this will just skip over them, but our paddle does. So it'll run the update. Now I wrote it this way just so you can compare what we're going to do in a second. Sometimes you want to go backwards through a table. So usually we start at 1 and go up to the end of the table. What happens if you want to start at the end and go to the beginning? You can do for I equals hashtag ents, the length of our entities table, start at the end at 1, and then you can do comma -1. This is an optional part of a for loop that I don't think we've used before. And it's how do you want to change that I variable every loop? And in this case, we want to do -1. It's 1 by default, but we want to move backwards. Local e equals ents I. We're going to move it on the vertical first. If our entity even has a vertical velocity and it's not 0, then we want to run this code. Move our entity. Don't move it on the X yet because we're going to do vertical first. Entity.dy. Do that same thing on the horizontal. If entity.dx and entity.dx does not equal 0, then move entity.dx 0. So first time, we pass in a 0 for the dx, we pass in its real dy. Second time, real dx 0. And then down in the draw, get rid of that. We're just going to do for e in all ents do if e.draw e:draw. Because the walls won't have a draw method, so we won't even try and call it. But for everything else, we'll have it draw itself. Look at that. And we can kind of like hit it with the side there, and we'll make that better in a little bit, but this is kind of fun. All right, we need to make some bricks. Function brick new, taking an X, a Y, and an image. I'm going to do this one a little differently. You'll see why. I'm going to do local b equals, and then at the end just return b. X equals x, y equals y, width equals, they're all going to be the same size. So half of our sprite is 16 across, half is 8. Our height, half of 8 is 4. I'm going to give them an HP of 1 because we want to be able to destroy our bricks. Some of them we want it so you have to hit them more than once. Image equals image for the sprite. We're going to give it a draw method, which we will write now. Function brick draw. There's a couple ways you could do this. I'm going to do it real easy. Sprite brick.image brick.x minus brick.width brick.y minus brick.height, and then just draw its second half next to it. So sprite brick.image plus 1 brick.x brick.y minus brick.height. Back in our main, in our init, let's put it down here after everything. We kind of just want like a block of bricks, a bunch of lines of bricks up at the top. We're going to do that with like 2 loops sort of inside each other. You could do this where you have nice, neat stripes. I'm going to make it random because we're gonna do something kind of goofy later. Okay, for y equals 16. So this is where we want to start. And we want to stop at 48, a y position of 48. And every loop we want to move down 8. Do. See how that's useful? Inside of that, for x equals 0, 127, every loop we want to move over 16. Do. Inside that, add to our nths table, brick new x plus 8, y plus 4, because we're kind of operating on like that upper left hand, just because that's how my brain sort of works and whatever, but then we need to offset it because it's got to be the center of the brick. And then I'm just going to do a random image, and we're going to make a little table here. Our numbers here, 16, 18, 20, 22, and 24. 16, 18, 20, 22, 24. That throws a bunch of bricks into our entities thing. Down here, we already wrote like the code to draw them and the code to collide with them because it's just working off of those methods that are built into them as entities. So they draw to the screen and they collide with the ball. And every time we hit Control R, we get a new random assortment of bricks. Now the point of breakout is that you break the bricks. And there's also a feature of breakout where you can sort of direct the ball depending on where you hit it on the paddle. If you hit it on the right side, it sort of shoots the ball to the right a little bit. It influences the direction of the ball, and we don't have that. So what we need is something called a callback. It's a method that an entity has that sort of gets triggered as part of an event. And we can have our physics system call that callback when something hits another thing. So in our move function, in our physics tab, in our move function, under resolve, if O dot on hit, O colon on hit, pass in entity. So when we move our entity, it does all this. If it collides with this other, and the other has an on hit callback, we call that method. We use the colon, so the first thing it'll pass in is that other thing itself. And the second argument is going to be the entity that is moving, that hit it, because we might want to reference it. All right, nothing has a callback yet. We got to make a callback. Let's start with the paddle. So we give our paddle an on-hit method. We'll make something called paddle hit. Function paddle hit. First argument is the paddle. Second argument is the other. If other.dx, then, because this will trigger when we hit the walls, but the walls, we don't want them to do anything. We only want to affect things that have this x velocity. If we hit dead center on our paddle, we don't want to affect the other's velocity at all. We want it to bounce normally. The further it gets right, the more we want to add to x velocity. The further we hit left, the more we want to subtract from its x velocity. We're going to do other.dx plus equals parentheses other.x minus p.x. So we get that difference between their centers divided by 16, just to sort of shrink the effect a bit. So now you can see it kind of speeds up. We can kind of like slow it down, right? Yeah, see that? And then we can like hit it back the other direction. So now we've got some like player agency. We've got ball control. In our brick, let's add a method on hit equals brick hit. Let's go make brick hit. Function brick hit itself and the other. Do brick.hp minus equals 1. Now we could say like if brick.hp is 0 or is less than or equal to 0, and then like delete it from the entities table right here. That could get kind of messy since we're like churning through all of these entities. If we like pull one out at the wrong time, the order might get kind of mixed up. What you want to do is like set a flag that this should be removed, and then do another pass later where you just pull out all the things that have this flag. So I'm just going to do b.remove equals b.hp is less than 1. And all this does is, in our brick table, set a Boolean called remove, this little bit of logic, if b.hp is less than 1, so if it's 0 or less, this is going to be true. If not, it's going to be false. So then later we can check if b.remove is true, then pull it out. So let's do that. In our main tab, in our update game, we're updating all our entities. We are moving and colliding. Let's do it right here since we started at the end and we're moving backwards. We won't like mess up the order if we pull one out. Just do remove. If e.remove, then, and you don't have to do like is equal to true. It's either true or false, or nil. If it doesn't even exist, then nil is the same as false in this case. So we're gonna do delete I, ents I. So since we're using I to get the position in the ents table, this is faster than using just del, because with del you give the table and the value, and it has to go through everything and check, is this the value? No. Is this the value? No. Is this the value? No. That's fine for like a few things, but if you have like a ton of entities, if your whole game is like doing this entity thing, it's way better to just be like, that one, that number, we have the number, go get them. All right. So yeah, now when we hit these, they disappear. Now time to find out, is Dave any good at breakout? The answer is no. So you might have noticed, if I like hit the ball on the side, it gets kind of nuts. Oh boy. But it doesn't really behave the way we want it to. It kind of like stops. Yeah. And if we like add another ball, it might not be so obvious, but like the way they collide, if I can get them to collide. This is like watching the DVD screensaver. It's the collisions aren't quite correct. I mean, we're doing like kind of stylized collisions anyway, but you know those like Newton's cradles where like guys in movies who have like big important business jobs. God, what am I talking about? They'll have like a big shiny desk and picture a CEO. He's got a big shiny desk. He's got one of those things and it's a bunch of like steel balls hanging, and you grab one, they clack, and then the one on the end goes, and they sort of go like. There's a concept called elastic collisions, and it has to do with like when things hit, how energy is transferred. We are going to do like a really simplified version of this here. If you want to do like the hardcore version, like the really cool version, there's a great YouTube channel called Coding Train. You can buy this guy's book. I'm going through this. It's real. It's pretty cool. But this is a good book. Great channel. If you want to get like hardcore, it's a different language, a little more complex. You might like recognize a bunch of it. You can get into that. It's pretty cool stuff. I made a little test project before I can just show off based on the Coding Train guys stuff. I made a little pachinko game here, and this is like actually simulated elastic collisions. This is more complex than what we're doing. Part of why we don't want to do it this way for our game is because it's more complicated. I don't quite understand all the math myself. It's also just like as a game, it feels way more random, which is appropriate for pachinko if you want something a little more predictable for breakout. So how can we do simplified elastic collisions in our breakout game? In our resolve function, we have this bounce. I'm going to put in if the other also has a y velocity, then all we're going to do is swap the two objects' velocities because they're the same mass, and we are doing the simplified checking. They're colliding horizontally or vertically, and you can just swap them like this: e.dy, comma, o.dy equals o.dy, comma, e.dy. So it just takes both of them, rewrites in the opposite. And then we'll do our else. And so if it's not that situation, we could work the restitution into this, but we're doing like a stylized thing here, so I'm not going to worry about it. And then we also do that on the x. If o.dx, then elastic collisions e.dx, comma, o.dx equals o.dx, comma, e.dx, else end. All right. Now it's a subtle change, I know, but it does matter. And I think, yeah, it feels a little better to hit it on the side. Like, so our breakout is a little strange because when you hit the ball on the side, it sort of hits the paddle back. Like it provides a little resistance there. It stops it like slows down the paddle, which I think is really fun. Part of what like You'll if you watch other breakout tutorials, you'll see sort of a problem where the ball can get like stuck in the paddle, or like you always have the ball, like if it hits kind of on the side, you just sort of teleport it up to the top of the paddle. And that's fine. Like for gameplay reasons, that can be good. Not the stuck in the paddle part. You don't want that, but like just sort of always teleporting the ball up, that can be like, oh yeah, I like really saved it. For ours, our like weird simulation version, I want this sort of, oh no, I just sort of whacked it on the side. Oh, this ball like got in my way. All right. Now, what if we want our bricks to behave differently? First of all, I'm going to get rid of that second ball. We've got it so that we've got a custom image for these different bricks. What we really want is a custom on-hit callback for each type of brick. So the nice thing about methods is, since this is a variable inside our entity table, if different entities have different callbacks, we can just swap out this variable the same way we change an exposition or an image. We can make it respond differently when it's hit. So I think what I'm going to do here, just to keep it simple, we make this local variable b, we set it up, and then I'm going to have a little bit of logic here that just edits it, depending on which image was set. It's going to be a little like handcrafted. It's fine for what we're doing here. If m is equal to 16, this one, then b.hp equals 2, b.onHit equals, and now we could write another function like down here, and if we wanted to keep like real organized, it might be worth it, but these functions are like so small, this is going to get so long. We can just like right here where we're doing this logic, we can just write a little function in here. And we don't even really have to name it. We're just like, this is your new function. So we can say b.onHit equals function, takes in b and o, and right in here, when it gets hit, we just want to change the b.image to 32, this broken one. And then we'll just run the standard brick hit. And that'll take care of that. We'll call that strong bricks. Let's just see if that works. So our normal bricks break in one hit. Strong brick cracks and is then removed. Cracks, removed. Else if image is equal to 18, then b.onHit equals function b other. What can this one do? On this one, I put little arrows. It'd be fun to like make the game harder. You move the paddle up. Since we assign the pad to a global variable, we don't have to find it. We can just do pad.y minus equals 2 and do the standard brick hit b comma o. All right. See what happens. Yeah. So we move up just like 2 pixels. It just makes it a little hard. We can do else if m is equal to 20, then let's make a smaller paddle. So b.onHit equals function b comma o. pad dot width minus equals 1 brick hit BO. Okay, so yeah, that shrinks just a little bit. So we just like well, move it up, shrink, move up. Now they don't all have to be bad for the player. So we'll do if image is equal to 22, then new ball. B dot on hit equals function b other. Add to ents ball new b dot x b dot y, so the brick center, and it'll be the other will be the ball that's hitting it, so negative o dot dx negative o dot dy, so it's going in like totally the opposite direction. Brick hit b comma o. Now that spawned like way more balls than we expected. And that is because since we are checking one direction then the other direction, and then we're setting that remove flag, and technically it's like still there, sometimes we're hitting it twice and doing the on hit callback twice. So all we want to do in our collide function we just want to make our first check. Hey, is this thing scheduled for demolition? Is that remove flag true? If not, then check collisions. And that should... yeah, so that's the appropriate number. Now we've got one more thing to write, and that is like a fail state. Because the balls just bounce off the bottom, and if they're down there, you should lose. So up here, in our main tab, we add these walls, and down here, when we add the floor, I'm actually going to move the floor down, like 145. And I'm going to give the wall an on-hit callback. I'm just going to write it right here, wall and other. When a ball goes down and hits that, I'm going to set its remove flag to true. And now we can fail. So let me get two balls. We can lose those. They don't come back. They don't bounce up. And now we've got like a real game here. Try and see if you can keep all these balls. Oh God. It's a little nutty. But yeah, it's a pretty fun and robust little arcadey physics thing. Now when we clear all those bricks, nothing happens. And I think I'm going to leave it to you to figure out what the next steps are. Because you know how to track score. You know how to make a simple scene manager. You could wrap all this up into a scene. You could have a title scene, a game over scene, a win scene. You could make a little check that goes through the entities. If there's no bricks left, then you win. If there's no balls left, then you lose. I bet, if you think about it, you could figure out how to make that scene manager after the win stage introduce a new level, randomize those bricks, or figure out how to arrange them in a different shape. You could draw more bricks. You could come up with more on-hit callbacks to do different things. Since the way we're spawning those bricks, we're using this R&D, you could change the weights. So if I add like 24, there's a way higher chance of it picking 24 when it picks a random one. So like now most of these are green, right? That could be, you could just change the odds of different bricks coming up depending on what level you're on to make it harder. Like imagine if they were all shrinking bricks and like maybe there was one that would like make it wide again that you're trying to get to or whatever. That could be fun. So I'll leave that to you. Just once recording this video, I want to do the breakout thing where you get up on top. Oh, come on. Oh my god. Yes. You know, with this entity system, you could even throw things in there that aren't bricks, that aren't balls. You could just throw in like obstacles. You could throw in like enemies or whatever. You could have like power-ups that fall down. And if they hit the paddle, then you collect it and something good happens, right? This is like a really flexible system that you can just sort of throw things into and define behaviors and have fun. So, all right, thanks for joining me. I'm gonna head out. Thank you so much. Have a good one.